Hi, we're here at Ontario Place presenting our paper on smart paddleboards and vehicles, and my name is Steve Mann.
I'm Ben Bimani. I'm Kamali Cabrera. I'm Samir Kagi.
Oh my God, look at that.
Yes.
See, when I pull on this, it spins the motors, it revs the motors up. And the idea is that I pull along and it sup follows behind me, so the paddleboard follows and carries my cargo while I swim.
So my name's Steve Mann, and I'm going to talk about smart paddleboards and other vayances. This is our paper on smart paddleboards and what we call vayances. And so in this paper, we're going to talk a little bit about how to make assistive technologies. With a shoulder and back injury, workplace-related injury, we have the issue of needing some help, assistance. So the first thing we tried was putting a motor here on the paddle itself, but that just increased the shoulder strain because you have to kind of bear that load on the shoulders. And also, a lot of times, depending on where you're paddling to, the situation, sometimes we swim over to ice. We do a lot of ice water swimming. We swim over to a block of ice, paddle, and until the ice disintegrates or whatever, and get on another one. And so in this case, the paddleboard, it can be a normal paddleboard or it might be ice. But in either case, we equip it with some sort of drive mechanism that senses the flexing in the paddle and thus gives assistance to help with this movement. And the other issue is sometimes when we swim, we want to be able to pull some cargo due to the back injury, shoulder injury. We want to make it a little bit easier to pull this load. So when we're going on cross-country swimming on long distances, we want to be able to pull heavy loads. And so there's a mechanism here which pulls, and the thing is we're pulling that load, and as the load is being pulled, we want to sense how much to drive on the motor. The amount of drive is proportional to the paddle flex. Now, one of the things we found is the derivative. We're off in the derivatives here. Like when we're controlling something, the accelerator is what matters. Force equals mass times acceleration, and therefore the acceleration is proportional to the force. And the motors provide force related to current. So the current control on the motor controls how much force there is. The accelerator is a voltage input that provides proportionality to the acceleration. But the thing we want is we want this thing to maintain a certain distance behind us. So we want to control distance or position or displacement. And really what we're in a sense giving it an acceleration. So if you look at this sort of hierarchy of derivatives, you've got acceleration here is the control point. And if you have a PID controller, a PID controller, you've got it including jerk and velocity, but none of those include the thing we want to control, which is displacement. So therefore, we propose the idea of a PIID controller, an extra derivative. And we really want to flank the thing we want to control, which is displacement on either side with its integral velocity and its derivative velocity and its integral displacement. We want to bound it on either side. So we really want a PIID controller. So we want proportional acceleration, and we want the integral, and maybe the derivative, which is jerk. So we invented or created this new kind of control system to be able to pull that paddle board behind us. And so this is the idea of the PIID controller is outlined in this paper. And so now we have this a concept of, a PID controller, PIID controller, and possibly a PIIDDD controller maybe. And in either case, we experiment with some of these different kinds of new controllers for controlling, triple integral, double integral, proportional, derivative. And then the other thing is, interestingly, to transport the paddleboard to the beach, we wanted a similar conveyance, and we did a similar technology here. We used a PIID controller because we found when we get off the bicycle and push it along the beach, there's a lot of them have a walk setting. You can hold down this button to put it into walk mode, but it only goes at a fixed speed. So if you've got somebody in front of you going really slowly, you got to keep stopping and starting. And so we needed something that would proportionate. So this allowed us to apply a constant proportion. And a PIID controller also worked for transporting the paddleboard to the beach, especially when you get off the bicycle and push it, because we had a force sensor on the handlebars that actually makes it work in this very similar way to the pulling the sup behind when we're swimming. Here's another variation of it, a pull wagon. So when we pull the wagon behind us, we're able to maintain a constant position of the wagon following us, a wagon that follows behind us. So we built a wagon that follows behind, and you can pull it and carry the cargo. But then we thought, well, wouldn't it be nice if that wagon went in front of you? So, you know, like something like this, where you're pushing something in front of you, like this for support. Wouldn't it be nice if that ran in front of you? So then the next thing that we started looking at is taking a device that instead of following behind you, it goes in front of you. It comes along in front of you and carries your cargo for you in front of you, and also gives you support if you need from the back injury. And at times you want to be able to not always have to have the support. When your back pain is less, you want to let go of it and run with it and let it lead you, and it becomes a leading device. And now it becomes a seeing aid as well, because it's equipped with cameras and LiDAR, and it actually provides you a seeing aid. So this vehicle of freedom of mobility, actually has expanded now to include not just things that follow you, but things that lead you, things that carry you. And for a person with a back injury also, not being able to sit down sometimes, not being able to sit on this vehicle. So then we're also looking at vehicles that you can control by laying down, like a layance, a laying down vayance. And so a lay down vayance, ideally, or the vision of the lay down vayance is something that I can use on land, in water, and in air. So I really want to be able to either drive or ride on the roads, cross water, and even fly in a laying down, facing down position. Not like a recumbent bicycle where you're facing up, but a forwards laying down position, which is a new mode of transport, a new method of transportation. So we have a lot of new ideas here, machines that will follow us, machines that will lead us, machines that will provide vision and seeing assistance. So a lot of my background is in vision and imaging and sensing and so on. This is the oscilloscope that my father got for me when I was 12 years old. It was broken. The time base didn't work on it. The dot only went up and down, and I was impatient and wanted to see it. So I put it on rollers like this so I could roll it back and forth. And I discovered something quite interesting when I had it connected to this police radar here. I discovered that I was able to see waves just sitting perfectly still. This was in 1974 when I invented something I called metavision, the vision of vision, sensing sensors and sensing their capacity to sense. Now, we started something called XV, the Extendiverse, through the IEEE. I'm connecting with some other people like Yu Yuan, president of the IEEE Standards Association, and Tom Coughlin, president of the IEEE, and we're sort of bringing forth this notion of XV, Extendiverse, whereas XR is this generalized framing. Like if you have reality and virtuality, sort of bits and atoms and bits, the physical reality is on the reality axis and virtual reality is on the virtuality axis. We've got here now physical reality, virtual reality, 100% physical, 100% virtual. And then, of course, we have augmented reality, which is both of these. You combine these together. And now there's a missing quadrant, which we call diminished reality. Technologies like dark sunglasses, welding glasses, things like that diminish our perception of reality. And so diminished reality is sensory deprivation. And in the extreme origin case, right at the origin, we ought to have a sensory deprivation tank, because that's when our input is zero. It doesn't mean our perception's zero, but it's when we have a signal input of zero. And so this VR float tank is something that I came up with many years ago, back in the early 1990s, virtual reality float tank, the world's first VR float tank. And the idea is that you take away everything sensory and then put in the virtual. And so this is a perfect example right here on this axis, on the virtuality axis only, a cold water swim, an ice water swim is a good example of the reality axis, and of course a good example of the in between, when you have both of these, is this sort of ice water swim with a VR headset. So now we can talk about extended reality, XR, which is to extend our perception of reality. And so this is some early work I did back in 1974, the world's first photograph of electromagnetic radio waves, perhaps. This is an example. This is Metavision, 1974, sensing sensors and sensing their capacity to sense, metavalence and metavision. This is a series of photographs of a surveillance camera taken with this strip of lights here that I made back in the 70s. And so this was an early example of metavision, the sensing of sensors and sensing their capacity to sense. Here's another example from the oscilloscope moving back and forth, seeing this with this police radar, a photograph of the sensing of sensing. The police radar is a sensor, and this is a sensor of sensors. And so this is meta-sensing, and this is metavision. These are examples of metavision and movalence here. Metavision with movalence, motorized sensing. And this is another example of movalence drone swarms. So this is some of the other related work we're doing. This is movalence here. This is a motor with a sequential wave imprinting machine on the motor spinning around. A couple of examples of that. This is a bicycle with a sequential wave imprinting machine on it. This is 2 microphones. We're seeing the interference pattern between the 2 microphones. XR definition, extended reality. This is from 1991, Charles Wyckoff and I. XR is any combination of a virtual environment with reality where the virtual environment is responsive to a real or complex valued output from reality by way of real-time computation. It can be analog or digital, doesn't necessarily have to be digital. And collaborative shared XR is what we refer to as XV, the extendiverse, when we start to share XR. XV definition, XV combines XR and as well as social computing. So if we look at it again in a children's blocks model, you've got atoms, bits, and genes. The bit of reality, virtuality, and sociality in this 3-dimensional plane, and XV comes out of the page here on XR. Shared XR, that's what XV is. And we went through some grand challenges, and we had a lot of fun. Thank you.